Well, there is more controversy surrounding the MTV show that is called
TV that includes he would have to
So this is a clip you guys have seen
jump
before.
several feet straight up into the air to avoid being hurt. It was impossible.
All right, so this guy's trying to jump over the car, right? So he's going to get hit.
He would have to jump several feet straight up into the air to avoid being hurt. It was impossible.
All right, so when I was discussing this, I said if the car is going at 30, the guy's going to move at 60, right?
He would have to jump several feet straight up into the air to avoid being hurt.
All right, so the object getting hit is always going to move nearly double the speed of the vehicle. All right, so here's a small demonstration of it. Here's a small demonstration of it. All right, so you guys see this. So notice that when there's impact, in this case, it's slowed down. It just moves out of the way. All right, my hand can go through it because as soon as there's impact, this thing is going to be moving at double the speed on my hand, give and take. All right, so if the car is moving at 30 miles per hour, the person getting hit is going to move at 60. If the car is moving at 40 miles per hour, the person getting hit is going to move at 80. The car is going at 50, the person is moving 100. The car is moving at 60, the person is moving at 120 miles per hour. Okay. I said I was getting those numbers from the conservation of energy momentum principle. All right, so I'll show you how that happens.
It was impossible.
All right, so action and reaction forces will be the same. Small mass is going to accelerate more. Larger mass is going to accelerate less. That's what it means. So as the person goes from the impact speed of the car, which is about 30 to almost 60 miles per hour, because the car is much more massive, the reaction force is going to be, while the reaction force is acting on the car is going to go from, say, about 30 miles per hour to about 29 to 28 miles per hour. So that's what we would expect to see. All right.
Well,
get those.
16-year-old boy stood in front of his friends.
So I'm going to turn this into a problem just to show you how it is done. All right, so I got this car, and the person is going to get hit by this amount of force. That's like 40,000 pounds of force acting on the person. This is the mass of the car. This is the mass of the person. The person is 150 pounds. So determine the final speed of the person. It's going to be double the speed of the car. It's going to be about 60 miles per hour. Determine the final speed of the car. It's going to be about 28 to 29 miles per hour. What is the change in momentum of the person, and what's the change in momentum of the car? So going back to the previous question. All right, I'm not going to take you through the derivation. This is for engineering and physics students. I'm going to go over the concept, not the derivation, because this derivation takes about an hour to do. Or in fast motion, it's going to be 3 minutes, but I'm not interested in derivation for you guys. Okay. So before the impact, the person is not moving, the car is moving. And after the impact, what happens? The car is going to slow down a little bit. The person is going to be moving double the speed of the car. Okay. So which means that we will have two unknowns. Okay. So you will know the initial speed of the car. You will know the initial speed of the person. And now you're interested in the final speed of the car as well as the person. So which means that you're going to have two unknowns. What that means is for two unknowns, you should be able to generate two equations. All right, during impact, just remember, I don't care what kind of impact it is, what kind of collision it is, the momentum is always going to be constant. It's going to be conserved. Here's your initial momentum. It's only the motion of the car, in this case. Here's your final momentum. It's the motion of the car as well as the person. All right. Now, because of the fact that we got two unknowns, all right, so those are your two unknowns. You need to have two equations to solve for two unknowns. So now you have to make an assumption. The assumption is if the collision is inelastic, there's no way you can generate a second formula. But if you make the assumption that the collision is elastic, then you can make the assumption. That's an underlying assumption, which means that kinetic energy is going to be conserved. So the total kinetic energy of the system before the impact is going to be the same as the total kinetic energy of the system after the impact. All right, guys, the algebra of this is kind of complicated, so I'm not going to show you the algebra. You need to have two equations in order to solve for two unknowns. And you get the second equation by assuming that the collision is elastic. All right. Real life collisions are inelastic. Making the assumption that it's an elastic collision, you're able to solve this problem. All right. So when you solve the problem, you end up getting the speed of the vehicle. So that's the speed of the vehicle. All right. So here's the initial speed of the vehicle. Here's the final speed of the vehicle. And here's the mass of the vehicle, is the mass of the person. All right. On the formula sheet, this is the formula that we have. So this is the formula that we got on the formula sheet. So this is object A. So this is the incoming vehicle. In this case, it could be the train, it could be the car, it could be a motorcycle. And so that's what we got. And the speed of the person who's getting hit comes out of this equation. And so that equation is also from the formula sheet. It's going to look like this. All right. So here's the speed of the car. Here's the speed of the person getting hit. All right. So those are the two equations that we will get to use. And both of them are on the formula sheet. All right. So, so equations will come out of the assumption. Let's say it's an elastic collision. It's an inelastic collision, but we assume that it is an elastic collision. So we end up getting two formulas for that one. So here's the speed of the car. The person is not moving initially. And so here's what happens right after impact. Here's the mass of the car. Here's the mass of the person. Initially, the car is moving at 30. The person is not moving. So what's the speed of the car right after impact? So what's the speed of the person right after impact? All right, so we got two formulas that we will get to use. Speed of the car right after impact is going to be given by this formula. All right, so putting the numbers in, end up getting something around 28 miles per hour. So that's what we expected. All right, so the car goes from 30 to 28 miles per hour, roughly. Speed of the person right after impact is given by that formula. Our expectation is the person is going to be moving nearly double the initial speed of the car, nearly. So it's going to be close to 60, but not quite. So we end up getting about 58 miles per hour. So that worked out. Okay, so almost double the speed of the car. All right, guys, these are, assumption was an inelastic, assumption was that this was an elastic collision. Inelastic collisions, the kinetic energy is not conserved. So what that means is instead of getting 28 miles per hour for the car, it's probably going to be close to 25 to 26. Instead of getting 58 to 60 miles per hour for the person who's getting hit, it's probably going to be around 55 miles per hour. Okay, so you can kind of eyeball stuff at this point. Okay, so the next question is, what is the change in momentum of the person? In this case, the car and the person. Okay, so going back to the rifle analogy that we were looking at, recoil that we were looking at. So what's the change in momentum of the car? What's the change in momentum of the person? Guys, before we do the computation, let me tell you what the answer is conceptually. Total momentum of a system is not going to change. Total momentum before and after will be the same. What that means is the individual change in momentum of one mass is going to be equal to the change in momentum of the other mass. Okay, whatever the momentum is lost by the car is going to be the amount of momentum gained by the person. So that's what it means. That's the way it should work out. All right, so if you look at the change in momentum of the person, all right, so the person is going to go from 0 to 58 miles per hour in terms of the metric units. So it's going to give you change in momentum in terms of a number. So this is the momentum gained by the person. Now, if you look at the change in momentum of the car, this is the momentum lost by the car. It's the same as the recoil of a rifle, right? So the amount of momentum gained by the person is the same as the amount of momentum lost by the person, the car that you end up getting. The total change in momentum of the system is going to be 0. When you add these two, you end up getting a 0. All right, so the last question is impact force. Last question is the impact force. What's the impact force if the impact lasts for 1/100th of a second? All right, so here from the impulse momentum theorem. All right, so the impulse changes momentum. Obviously, you know the change in momentum of the car as well as the person. All right, so the change in momentum of the person is going to be this. All right, so that's the amount of force acting on the person. Change in momentum of the car is going to be this, except it's going to be negative. All right, so this becomes the action force. This becomes the reaction force. So action and reaction forces are the same. In terms of pounds, it's going to be 40,000 pounds. All right, so it worked out beautifully. Everything worked out. Okay. All right. Okay, let me show you 3 different applications of this.
Next.
I mean, you guys are just finding, notice that when you actually rephrase and reframe everything within the context of momentum, there's a lot more to the collisions and impact and just increasing the impact time and reducing the acceleration. This is really, really rich.
Detective Walstead reveals the secret behind this game, where you have to get the ball to stay in the tub.
There's one game that I see very frequently, almost every carnival, is that bushel basket game. And that just annoys me because I'll stand back and watch, and I'll watch people walk up and get cheated, because you can't win the game the way it's set up. The player stands back at such a distance, and the angle of the basket, you cannot win, and the ball won't stay in there.
You want to give them the impression that there is a chance to win, and it's a good chance. And in reality, there's no chance to win. Sometimes the carny will reel you in with a free throw, but you can bet that's usually rigged too.
That's the classic scam right there. What he does is he puts the ball in ahead of time and tells her, go ahead, you throw one in for practice. And what happens is her ball goes in, hits the one that he put in there, and then hers will stay in. But when out comes her money, out comes that other ball, I guarantee it.
And now here's another game of chance. Fat chance is more like it.
The object of this game is to knock down both Coke bottles in one roll of the ball. It can't be done because what the guy does is he'll actually nudge one of the Coke bottles slightly in front of the other, maybe an eighth of an inch, quarter of an inch. So what happens is when you roll the ball into it like that, the ball hits one of the bottles there, you can clearly see one's in front of the other, and there it went. The energy from the ball was absorbed in the first bottle, leaving nothing for the second bottle.
All these little scams add up to big money.
Okay, so let's go back. Let me highlight.
You want to give them the impression that there is a goal in the basket, you cannot
So you got the bushel basket.
win, and the ball will stay
Reality, the ball will never stay.
in there.
Okay, 100% of the time, it's not going to stay. They're going to create the illusion that
You want to give them the impression that
only way they're going to create the impression that you can do
there
this.
is a chance to win, and it's a good chance. And in reality, there's no chance
I love the fact that,
to win.
oh, this is mysterious. Only way they're going to create the impression that you got a chance, provided that they place a ball in.
Sometimes
And somehow, if you can hit this ball,
the carny
the one that you're throwing, it's going to
will reel you in with a free throw, but you can bet that's usually rigged.
it's 100% right. Okay, I'll show you reason why. If there's a ball that's going to remain there. If there's no ball, it's going to bounce back out. The other one,
The object
this one.
of chance.
the guy does is he'll actually
All right, so
nudge one.
it doesn't matter. He ends up nudging one of them slightly in front of the other one. Even if you saw that happen, you wouldn't think much of it.
The co-pilot slightly in
Doesn't matter how hard you throw this
front of the
ball.
other, maybe an eighth of an inch, quarter of an inch. So what happens is when you roll the ball into it like that,
Doesn't matter how hard you
the
roll
ball
it.
hits one of the bottom.
This ball is always going to come to a stop. It's never going to be able to hit the second one. And there's a good reason for it. And so let's focus on that for the conceptual portion of the test next week. Okay, there are three cases that we will deal with. Right. Three collisions, three different collisions. Number one, the incoming mass is going to be much bigger than object getting hit. All right, it's like train hitting a person. All right, so the train hitting a person. Person is about, what is this, 170, 150 pounds or something. Train is 10, 20, 30 million pounds. All right, that's the case that you're looking at. Okay. If the train is coming at you at 60 miles per hour, what do you expect? The speed of the train is going to be about almost, it's going to remain at 60. It could be 59.999 miles per hour. The person's speed is going to be double the speed of the train. So it's going to be about 120 miles per hour. Okay, so that's what you would expect to see. So the train is going to be much more faster than the person is. Okay, now the trick to interpreting this is the person's mass is very small compared to the train, so it's negligible. We say it's ignorable, it's negligible. So you just say ignore it. Okay, so if you ignore it, only mass that you have to focus on is the mass of the train. So the mass of the train divided by the mass of the train is just going to cancel out. So the initial speed of the train and the final speed of the train is more or less the same. So train is coming at 60. After the impact, train is moving almost 60 miles per hour, almost, slightly less than that. Right, so that's the case number one. So what happens to the person? I said the person is going to move double the speed of the train. Once again, the person's mass is significantly small, so the mass itself is insignificant. So just ignore that because we want an estimate. Notice that the mass of the train is the dominant term, so masses will once again cancel. Notice that the person is going to be moving roughly about double the speed of the train. Okay, so roughly about double the speed of the train. So the train is going at 60. Now the person is moving at 120 miles per hour. So that's the case that we discussed. What if the masses are the same, like the billiard balls? What if the masses are the same? Okay, so I'm trying to make a decision. Okay, what if the masses are the same? If masses are the same, mass A is going to be the same as mass B. Okay, guys, if masses are the same, what happens here? Okay, m minus m is going to be 0. All right, so which means that this is the first billiard ball approaching at a given speed. So what happens to the speed of this billiard ball hitting this mass? It'll come to a stop because masses are the same. So what happens to the second billiard ball? Now let's go on to this one. All right, so you got the masses are the same, so 2 times this mass plus m is going to be again 2 times the mass. All right, so they will cancel, so you end up being 1 there. So which means that the second billiard ball is going to move at the speed of the first one. All right, so the first billiard ball is going to come to a stop. The second one is going to start moving at the speed of the incoming one. Okay, so you know what that means, right? What that means is the baseball and the Coke bottle, they have identical masses. So it doesn't matter how fast you roll the baseball, because they got identical masses. That velocity is going to get transferred to the Coke bottle, and then this one is going to come to a stop, and the other one is going to keep moving. All right, and then the bushel basket thing goes like this. Okay, so here's the small mass. It's the mass of a baseball. Here's the big mass. The big mass is going to be the wall that you're looking at. Okay, so the baseball is going to be, the mass of the baseball is insignificant compared to the mass of the ball. Okay, now how do we do the interpretation? This time, mass of the baseball is going to be ignorable, so that term is going to drop out. Okay, so if you ignore the mass of the baseball, so what happens? The mass of the ball is going to cancel, it's going to be 1. So which means that the coming ball is going to bounce and it's going to go in the opposite direction at the same speed. So the final speed of the ball is identical to the initial speed of the ball, except there's a negative sign, so which means that the ball is going to move in the opposite direction. All right, here, the mass of the ball is insignificant, so compared to the wall, so you can assume that to be 0. So that term is going to become 0. So the masses will become 0. So which means that the speed of the wall is going to be 0. So wall is not going to move. That's what it means. So what happens? The wall doesn't move. The ball bounces back. It bounces back out of the bushel basket at the same speed. Okay, that's it. So everything has been nicely explained. Okay.